This alternating series, the b part is n over 5 to the n. With a function like n over 5 to the n, we can see that it's increasing. This problem doesn't ask me to actually prove that it converges, but with a 5 to the n in the denominator, that is going to be so huge, it's going to make these fractions so small, it's obvious that it's going to converge. So this is the function x over 5 to the x, and my limits right now are tiny, 0 to 0.0002, and the function is definitely going to 0, and it's definitely decreasing all the time. Okay, so my job here is to actually then estimate the sum to be within 4 decimal places. So let's say that the overall answer is A. So that's the total sum. Then there's the remainder theorem that says, here, add up all of these fractions as they drop down, add up all of these fractions. And suppose that you add up to the nth term as an estimate. So you say, okay, add up the first n terms. Then the remainder theorem says, how much are you going to be off by? Or in other words, what's the remaining part going to be? So then it says the difference between the actual answer and your estimate is going to be less than or equal to whatever this next term is. B n plus 1. So the difference between the actual answer and your estimate will be less than or equal to that. Now in this problem I'm being asked to be accurate within 4 decimal places. That means that my error can be 0.0001. Oh, actually, that has error in the 4th decimal place. So the first 4 have to be accurate. It's the 5th one that could have a little bit of error. And in fact, the 5th one could have as much error as a 0.9, as long as the first 4 decimal places are correct. So that is my error. Could be that much. Well, this is saying how much are you off by? It's going to be at most that much. So in other words, this is the error. So the next thing to do is say when is b sub n plus 1 equal to a 0.00009. Well, b n plus 1 means go to this thing right here and substitute an n plus 1. So you have n plus 1 over 5 to the n plus 1. When does that equal 0.00009? Since this function has exponentials, you would have to use logarithms to solve it. Since it has algebra, you would have to use the rules of algebra. 2 different systems. So we're then going to use the calculator to figure this out. So we have x plus 1 divided by 5 raised to the x plus 1. And we need that very, very small. So let's say the x's can go from maybe the first 10 terms or so. This needs to be very small, so I could have it go to 0.0002. Should do it. And then graph. So there goes the exponential function. Wow, it's so small the calculator's rounding it to 0. But I don't see my line. Oh, I didn't put my line. 0.00009. Then when do those two intersect? So that's right there. So we could find out the exact point where they intersect. So that's when n plus 1 equals a 6, essentially. So that was for n plus 1. When n plus 1 equals a 6, so in other words, when n equals 5. So then what that's saying is, if you want this to be the maximum error, you're going to have to add up 5 terms. So go to this alternating series, and add up the first 5 terms. So I'm going to use sum the sequence -1, and then it's n over 5 to the n, with n going from 1 to 5. So we need sum sequence, forgot my n right there, -1 to the, right now the calculator's in x mode, so that's fine, and then times x divided by 5 to the x, with x going from 1 to 5. So then the answer is tiny. Wow, 0.00000, etc. and then a number, or in other words, it's -2.98 times 10 to the 17th.